Welcome all the students in YouTube channel of TC Chauhan sir, Physics. We shall discuss about 12th board special, in which today we discuss about Kirchoff's law and its application. It is main part of electro current or current electricity, and in this part several useful questions, either small questions or big question, can be asked. We shall discuss about several questions and applications. First of all, what is need of Kirchoff's law? Kirchoff's law was given for the complicated circuits where Ohm's law fails. According to Kirchoff, there are two basic laws. These laws are current law and voltage law. First of all, we shall discuss about current law. Current law is also known as node law or junction law. What does it mean by this first law? When there is a junction or node where several currents are going to meet, like that. These are several branches which are meeting at point O, and several currents are I1, I2, I3, I4, I5. Few currents are towards the junction and few currents are away from the junction. Then this law indicates that the algebraic sum of all the currents at a junction at a node is always 0. Sigma I is equal to 0. The question is, which conservation law is followed by this law? Then the answer will be this first law, or Kirchoff first law, follows law of conservation of charge. It means the net charge coming towards the junction will always be net charge going outward the junction. For example, we are taking currents. Current I is toward the junction. You take positive sign I1. For I2, again positive sign because it is toward junction. While I3 and I4 are away from the junction, so there will be negative sign. I5 is again towards junction, so that will be positive sign. This is all about the first law or junction law or node law. This law is useful whenever you have to find the net current passing through a certain region. Like we take an example. This is supposed to be a current. I1 is equal to 5 ampere. This is another part through which current I is required to be determined. This is another part in which current 2 ampere is toward the junction, and this is another part in which current 1 ampere is going away from the junction. As I have told you that according to first law, sigma I should be 0. That means I1 which is coming toward taken positive, I which is 2 ampere which is toward the junction taken positive again, 1 ampere which is away taken negative, and I is away taken negative. Minus I is equal to 0. You will have 5 plus 1 6, then I is equal to 6 ampere. This current which is required to find is 6 ampere and it is away from the junction. This is about the application. Now what about the second law? According to this law, in a closed loop carrying a particular voltage source or a particular resistance, net EMF in a particular direction will always be equal to algebraic sum of net potential difference taken in the direction and in concept of resistances. Like there are few cells which are taken as EMF sources. There are few resistances. The cells are connected in this way that these are giving current such that the net current go on increasing. The direction is very important here. We are taking A, B, C, D. It is a closed loop. It is applicable for closed loop only. These are resistances R1 and R2. These are EMFs E1 and E2. If we are taking the loop in this way, then along loop always take current for negative sign. Then algebraic sum of EMF in a particular direction will always be algebraic sum of potential differences in that direction. This always follow conservation of energy. Now the question arises, in which way current will flow? You know, the first cell which is giving current in this direction, second cell also in this direction. So overall current will show in this direction. Suppose it is I, it is I. Then how to make the equation according to this formula? Sigma E is equal to sigma V. All EMFs are taken along which then it will be E1 taken negative and E2 also taken negative. Along the direction of current we have to take negative sign. This is law. Now potential differences we are taking the direction along the direction of current, then negative sign we have to take minus R1 minus R2. Then you will have E1 plus E2 is equal to negative sign is taken common both sides, then IR1 plus IR2. This is all about the algebraic sum of EMFs is always equal to algebraic sum of potential differences. Question arises, when there is no EMF source present, what happens? If EMF source is not present, then take algebraic sum of EMFs to be 0, but algebraic sum of potential differences will be there. So we can say that as a result, in a particular loop, the potential difference across resistances will be 0 taken in sum. Like we are taking an example. This is a loop, closed loop, and here A, B, C is its points. Current I is coming here. This part is supposed to be I1. This part is supposed to be I2. This current will pass in this way, and we have to take a loop that is closed loop, should be A, B, C, A. According to this loop, sigma V is equal to 0 because there is no EMF sources. Now sigma V, we are moving in this way, A, B, C, A. Then what happened? Along the direction of current, I have told you that take potential difference negative. Then minus I1, this resistance is supposed to be R1, this is supposed to be R2, this is supposed to be R3. Then minus I1 R1 minus I1 R2. This current is I1 still, but when we are moving away, then this will be opposite. So plus sign will be there, and this sign will be I2 R3 is equal to 0. You can take negative sign common. You will have I1 R1 plus I1 R2 minus I2 R3 is equal to 0. This is important as far as we concern several numerical problems. We can take example on this basis. The example is, if we consider this is an EMF source of 2 volt. We consider there is a resistance 2 ohm along with it. There is another EMF source which is of 1 volt and resistance is supposed to be 1 ohm. This is another resistance. It is supposed to be 5 ohm. We have to find current in each part. Then you should apply the law which is Kirchoff's law, that is Kirchoff first and second law. Now according to first law, this is supposed to be current I1, this current is supposed to be I2. The total current first law will give I1 plus I2. This current is divided again in initial parts I1 and I2. Use Kirchoff second law in this part initially, then you will have sigma E is equal to sigma V. Sigma E, that is sum of EMFs, and it is 2 minus, suppose this is 1 volt, then 2 minus 1 is equal to 2 I1 minus I2. This is equation number first. To solve its part, you have to take another equation. Let us take this equation. In second loop, we consider sigma E is equal to sigma V, and according to this, the algebraic sum of EMFs is 1 volt. Algebraic sum of potential difference will be 5 into I1 plus I2 plus 1 into I2. So these are two equations By solving these equations, you will get the results, that is I1, you can get I1, you can get I2, you can get total current I is equal to I1 plus I2. So Kirchoff's second law is very useful when we consider such problems. Now, what is application of Kirchoff law? The first application, the primary application is Wheatstone bridge. What does it mean by Wheatstone bridge? Wheatstone bridge is a particular bridge used to find the unknown resistance using three known resistances. This is a kind of Wheatstone bridge. Its application can be taken according to this. These are four resistances along four sides of a square, P, Q, R and S. This is galvanometer. This pass a current Ig through it. This is EMF and this is one-way key. This indicates that in equilibrium state, in balanced state of Wheatstone bridge, P upon Q should be equal to R upon S. Then current through galvanometer Ig will be 0. Listen again, it is very important. Wheatstone bridge is a bridge or a particular arrangement of four resistances in which four resistances are kept along the arms of a square. One diagonal contain galvanometer and key, other diagonal contain cell and key, and the balanced state of Wheatstone bridge is ratio of P upon Q is equal to R upon S, that is ratio of sides or the ratio of resistances along sides that is equal, then the current flowing through galvanometer will be 0. This is all about the WSB or Wheatstone bridge. Now, what is application of Wheatstone bridge? Wheatstone bridge is very useful in determining unknown resistances. Suppose this is a Wheatstone bridge. Listen it carefully. This P, Q, R and S. A student wants to solve a numerical question on this basis. He is given particular resistance 3 ohm, 7 ohm, 2 ohm and X ohm. Then how to find this X ohm if current through galvanometer is 0? What is the way? The only way is its balanced state P upon Q is equal to R upon S. What is P? It is 3. What is Q? It is 7. What is R? It is 2. And what is X, which is required to find? Just put the balanced state, get the result. X is equal to 14 by 3 ohm. This is about the application or use of Wheatstone bridge. Now we shall discuss another application of Wheatstone bridge. You are having a Wheatstone bridge in this way. It is having a particular galvanometer. It is 2 ohm resistance. It is X ohm resistance. It is required to find. It is 6 ohm resistance. It is 1 ohm. It is 2 ohm. Now how to find value of X? It's very simple. These two are taken in series. Just take it in series. 2 plus X upon 6 P upon Q should be equal to R upon S 1 upon 2. Just solve it. You will have X is equal to 3 minus 2, that is 1 ohm. So it is very useful in several aspects. Now the question arises that what is practical application of Wheatstone bridge? It is meter bridge. Meter bridge is in fact a device having 1 meter long resistance wire and working on the principle of Wheatstone bridge. This is like a practical device having 3 copper strips. These strips are A, C and B. Now, a resistance wire which is of 1 meter is kept in between A and C, and there is another device which is called galvanometer connected here. Here there is a resistance box connected through which known resistance is taken out. There is a unknown resistance S here. Here we can use a cell or key. This point is supposed to be D. If this length where galvanometer shows zero difference is supposed to be L, then this will be 100 minus L. Now the question arises, what is balance state of meter bridge? Meter bridge balance state is P upon Q is equal to R upon S. It is identical to balance state of the Wheatstone bridge because it works on the principle of Wheatstone bridge. Just put the values, you will have unknown resistance S is equal to 100 minus L upon L into R. Here the unknown resistance P is supposed to be sigma into L. Sigma is resistance per unit length. Unknown resistance Q is supposed to be sigma into 100 minus L. These are few values on which it is based. So this is about meter bridge. The numerical question based upon meter bridge is, if you are given balancing length for a particular resistance of 5 ohm supposed to be 60 centimeter, then find the unknown resistance used in other gap. What about S? I have told you earlier the formula S is equal to 100 minus L upon L into R. Then 100 minus, you have to take it in centimeters because 100 is in centimeter, upon 60 into 60 into R is 5. Just simplify, 40 upon 60 into 5. That is 20 upon 6 or 10 upon 3. So it is very simple. Whenever you are given a balancing length, whenever you are given a particular unknown resistance. So this was the session about Wheatstone bridge, about meter bridge, about Kirchoff's laws. So students, it will be beneficial in forthcoming board examinations. Thanks a lot. If you like this, you should like, subscribe and share our channel. Thank you very much.